Lesson 3 of Chapter 6 will deal primarily with solving equations where we have what are called multiple angles. Multiple angles is when we don't have simply a theta or an x inside of a trig function, but instead we have multiple variables such as a 2 theta or a 3 theta or a 4x, something like that. And we'll also encounter for the first time where they don't give us restrictions. On this first example, you can see that they did specify degrees, so we are in degrees, and they did specify that we had restrictions. However, if you look inside the cosine function here, you can see that we have a 2 theta. Since we have a 2 theta, we need to realize that that entire restriction has been multiplied by 2. If I multiply that restriction by 2, 2 times 0, of course, is still 0 degrees. 2 times theta would be our 2 theta that we want, and 2 times 360 would be 720. So although theta is within one rotation, 2 theta can go 2 rotations. And we'll utilize that fact as we go through and do these problems. Now, if you look here, the trig function is already isolated, so we're at the point where we decide if it's a reference angle or if it's a quadrantal angle. This one happens to be a reference angle again. And the cosine being square root of 3 over 2 corresponds to a reference of 30 degrees. We have a negative cosine. Negative cosine occurs in 2 quadrants. It occurs in quadrant 2 and in quadrant 3. Now, on rotation 1, so the first rotation, in quadrant 2, our 2 theta, the inside of that trig function, will be equal to, well, once again, it's in quadrant 2, so we'll take 180 and subtract the reference angle. 180 minus 30 gives us 150. And then our quadrant 3 angle on the first rotation, our 2 theta once again, will be equal to, now this time we have to add the reference angle again to the 180, and we get 210. Now these aren't finished yet, but we'll come back to them in just a little bit. Let's talk about the second rotation. On the second rotation, well, we're adding a full rotation, which is 360 degrees, to our 150 degrees. So if we take 360 plus 150, then in our second quadrant, we have 510. So in quadrant 2, on the second rotation, the 2 theta will be equal to 510. If we do a similar thing in the third quadrant, we add 360 to the 210, we end up with 570. Now, none of this is finished yet because we actually need to solve for theta. So when we go back to our first rotation, we would have to divide each of these by 2. So we end up with theta equals 75 degrees. And if we divide this one by 2, we get theta equals 105 degrees. And if we do the same thing here, 510 divided by 2 comes out to be 255 degrees. And likewise for our final answer, 570 divided by 2 comes out to be 285 degrees. You'll notice that all of our theta, all of our true answers did end up within that first rotation, 0 to 360. And that's how we'll handle multiple angle situations. Let's take a look at a second example with multiple angles. In this one, yet again, we're in degrees. This time we have 3 theta, so we'll be multiplying these restrictions by 3. So 3 times 0, of course, is 0. 3 times theta is our 3 theta that we desired. And 3 times 360 is 1,080. So you can see that 3 theta can go 3 rotations. And we'll utilize that. Now, this one is already, again, solved for the trig function. It's already isolated. It also is quadrantal. The quadrantal angle on the first rotation that has a sine that's equal to -1. Well, sine is, of course, y over r. And the only quadrantal angle that has a y that's -1 is 270. So on the first rotation, the only answer is 3 theta equals 270. Now on the second rotation, we're going to be taking 360, which is a rotation, plus an additional 270. So we end up with 3 theta equals 630. And on the third and final rotation, we'll add yet another 360 to that 630, and we end up with 990. So 3 theta is equal to 990. Now keep in mind, none of these are our answers yet. We have to go through and we have to divide by 3 on each of them. So if we divide by 3 on this first one, we get theta equals 90 degrees. If we divide by 3 on the second one, we get theta equals 210 degrees. And if we divide by 3 on this last one, we get theta equals 330 degrees. You see how the multiple angles were handled there? Let's take a look at a third example. Now, in this third example, it tells us that we're working with radians. But it says to find all solutions in radians and does not give us any restrictions. Since there are no restrictions, there will actually be infinite answers. Now, we begin the exact same way that we always have before. We try to isolate the trig function, and as you can see, the trig function is already isolated. And you'll notice that once again, it's a sine that's equal to -1. We just did that. That's a quadrantal angle. Up above, we said that that was 270 degrees. Now, in radians, 270 degrees corresponds to 3 pi over 2. So, on our first rotation, the 5x would be equal to 3 pi over 2. Now, that's on the first rotation, but we can add any number of rotations we want. Each full rotation adds 2 pi radians to it. So we can add any multiple of 2 pi. To show that, we'll put plus 2 pi times n. N stands for the number of multiples. Now, sometimes they'll use the letter k for the number of multiples. It really doesn't matter which one's used at all. Of course, this isn't finished yet. To finish it, you would have to divide everything by 5. If I divide by 5 here, dividing a fraction by 5 can be accomplished most easiest by just multiplying the denominator by 5. So that would be 3 pi over 10. And of course here we have to divide by 5 as well. And this would handle or account for all the possible infinite solutions. So when it doesn't give us a restriction, a certain number of rotations, you'll always have something added on the end that has a variable in it. The variable can't be the same variable that's in the problem. It's usually an n or a k, and it stands for the number of rotations that have been gone through. Let's try another of these. So if we look at this one, once again it says to find all degree solutions rather, and there are no restrictions. This one is one where we're going to have to factor, but we factored this before. We'll use a 2 sine of 3 theta, and then a single sine of 3 theta. The back ones, of course, have to be 1. And to end up with a negative in the middle, I'll need to put a negative here and a positive here. And as we've done before, we'll set each of those factors equal to 0. To isolate the trig function in the first one, the left one, we'll subtract 1 and divide by 2. We get sine of 3 theta equals negative 1/2. For the right one, we just have to add 1. Sine of 3 theta is equal to 1. Now this first one actually ends up being a reference angle, and we're in degrees. The reference angle in degrees where the sine is equal to 1/2 is 30 degrees. But we have a negative sign, and a negative sign will occur in, well, it occurs in quadrants 3 and quadrant 4. So we'll have a quadrant 3 answer, and then we'll also have a quadrant 4 answer. For the quadrant 3 answer, the 3 theta, the inside of the trig function, will be equal to, and in this case, we'll have to add 30 to the 180 degrees to get into quadrant 3. 180 plus 30 is 210. But because we can have infinite solutions, we'll have to add multiples of, well, in this case, a full rotation is 360 degrees, so multiples of 360. So plus 360n. Now we'll come back and finish that in just a moment. For the quadrant 4 solutions, our 3 theta will be equal to, now in this case, we'll have to subtract 30 from 360, so we'll end up with 330 plus, once again, our 360 times n. The 360 times n corresponds to adding full rotations. Now we'll come back and finish each of those in just 1 second, but if you look at the right factor, sine 3 theta equals 1, that one is quadrantal. And the quadrantal angle that has a sine equal to 1 is 90. So we will have 3 theta equals 90 degrees plus our 360n. And then we have to go back and finish each of them. So to finish each of them, we divide by 3. If I divide everything by 3 on the quadrant 3, I get theta equals 70 plus 120n. That would be one of our solutions. Quadrant 4, I would get 110 plus 120n. And finally, the quadrantal one, I would get 30 plus 120n. All 3 of those would stand for our solutions to this equation. One last example here in this lesson, and this one again asks us for all degree solutions and has no restrictions. Now at first glance, this one looks like it's much more complicated than the ones we've done before, but it actually isn't much more complicated. In fact, the trig function is already isolated, and we do have a reference angle. The reference angle in degrees, where sine is equal to square root of 3 over 2, would be 60 degrees. We have a positive sign, which means we have 2 quadrants, and it would be quadrant 1 and quadrant 2. The quadrant 1 angle, well, we take the entire inside of the trig function, the 2a plus 50, and in quadrant 1, that would be equal to our reference angle on the first rotation. And then we would add multiples of 360 because we can have infinite rotations. In quadrant 2, the entire inside of the trig function, sorry about that, the 2a plus 50 would be equal to, now in quadrant 2 we would have to subtract 60 from 180, so we'd get 120 plus 360n. Now these are not our answers. In fact, we have a couple steps left to go. The first step that we would need to do is we would have to subtract 50 on both sides. I would subtract the 50 here and subtract the 50 there, because those are like terms. That would leave me with 2a equals, and 10 degrees plus 360n. And now I'd have to divide everything by 2. So a would equal 5 degrees plus 180n. That would be considered one of our solutions. Doing the same type of thing over here, we would subtract 50 on both sides. Oops, sorry about that. We'll subtract 50 on both sides. That would leave us with 2a is equal to 70 plus 360n. We would divide everything by 2, and we would have a equals 35 plus 180n. And that is how we handle multiple angles when we're solving trig equations. Again, if you need to go through this a couple times or pause it and look at it, please feel free to do that. If you have questions, remember my office hour link using the Teams app.